Hi students, in our previous videos we had discussed about the chemical reactions of alcohols, and still in the same chemical reactions of alcohols we are there in the last chemical reaction, that is with dehydration of alcohols. In this process, from the alcohol molecule, a molecule of water will be eliminated. Means it will be eliminated in the presence of a protonated acid. Generally, we take sulfuric acid in the case of a primary alcohol. There are two acids that we use here. One is called concentrated sulfuric acid or H3PO4, phosphoric acid. These are going to give the H plus ions in the reaction. They will be generating the H plus ions in the reaction, and we are going to observe, if you choose a primary alcohol, we are going to take that the primary alcohol is going to lose a molecule of water. Like you can use CH3, CH2OH. That is what we call generally as ethanol. In this, OH bonded carbon was directly bonded to only one carbon. Once you are going to add the concentrated sulfuric acid for this ethyl alcohol or ethanol, the concentrated sulfuric acid will give H plus ions, and they will be generated at a high temperature of 443 Kelvin. At this temperature, the OH of the CH2 bonded and one of the hydrogen from the beta carbon, this is we can call alpha carbon and beta carbon, the OH will be eliminated along with hydrogen of the beta carbon by the formation of a molecule of water. The remaining are, here there is an electron carbon and another electron carbon, resulting a double bond between carbon and carbon. Means ethanol on dehydration in the presence of sulfuric acid, it is forming ethene. It is forming ethene. The same we can carry, but now we are taking one secondary alcohol like CH3, 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 OH. Can you give any name for this compound? There are three carbon atoms, so the longest chain is propane, and alcohol group is its second carbon, so we can call this one as the propanol or propane 2-ol is the exact name. Now, in this case, we are going to use the phosphoric acid. When we are going to use the phosphoric acid, it can be achieved. Which can be achieved? Dehydration can be achieved at a very low temperature than in the case of primary alcohol. Here, imagine this is the alpha carbon and here we have the beta carbons. So, the OH group will be eliminated along with any of the beta hydrogen. That's the esteric hydrogen. So, the hydrogen I am choosing from the first carbon. It can be done from the third carbon also because both are symmetric. Just I am choosing from the first carbon. Means the OH bonded CH is going to form a double bond with CH2. In this case, the elimination of water molecule has also been taken place. What is the name of the compound we can give? Pro 1E. Pro 1E. In the case of secondary alcohol, we got the alkene, but at a low temperature. We can get the same type of alkene when we use a tertiary alcohol. Before we go for the tertiary alcohol, remember we are going to take here only 80% of H3PO4 percentage. We have already learned in the chapter solutions. Means 80 ml of phosphoric acid is present, 20 ml of water will be present in the solution. That's called as 80% of phosphoric acid. That is used in the case of secondary alcohol. But if you use a tertiary alcohol like CH3, 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 OH. Can you give a name for this compound? Yes, the longest chain is 1, 2 and 3. So the name is 2-methyl propane 2O. Here the OH bonded carbon got 3 alkyl groups and it is a tertiary alcohol. In the case of tertiary alcohol, we are using the same phosphoric acid but at a very low temperature than the expected, only 349 Kelvin. Here the phosphoric percentage is also very less. Means what we are going to speak is when we are studying the type of alcohol, primary is going to react at high temperature, secondary is going to react at just low temperature than the primary, tertiary is further reacting at a very low temperature than the secondary. Then in this case, what will be the product? Let us see. The OH is bonded to a carbon. In return, it is bonded to 3 other symmetrical carbons. So you can remove hydrogen from any of the beta carbon. So let us see here. I want to call this one as CH3. I am removing hydrogen from here. CH2. CH3. So this is the product that we got here, along with a molecule of water. By this, what we are going to conclude is the reactivity order of alcohols for dehydration is given as tertiary is highly reactive than the secondary, that is highly reactive than the primary alcohol for the dehydration reaction. Now let us see the mechanism how this dehydration reaction takes place, and this mechanism we are going to take an example of how to convert ethanol into ethene. That's the only mechanism that we are discussing in this video for converting a primary alcohol into an alkene, that is the ethene. So let us take down the mechanism, how it goes on. So let us see the mechanism of dehydration of ethanol to ethene. Initially, this will be carrying in 3-step mechanism. That's the point we need to consider. And this point, the first and foremost thing is the concentrated sulfuric acid will be the proton donor in this equation. situation. That will give the H plus ion. So let us see the H2SO4 that we had used in this equation. It is going to give the H plus ions and the remaining byproduct is HSO4 minus. This is what we call as the proton ion, protic acids. What do we call this as the protic acids? In the step 1, the ethanol that we had used, on oxygen there are 2 lone pairs. It will be protonated. Which is going to be protonated? Ethanol is going to be protonated because this is an electrophile and the lone pairs will be donated for the electrophile. So the step 1 we call protonation of ethanol. Protonation of ethanol. Then after donating the lone pair, we get the oxygen with 2 hydrogens bearing a positive charge. This is we call as the ethyl group and the oxonium ion. We call this as the ethyl oxonium ion. Now the oxygen need to utilize its positive charge. Hence it is going to withdraw the shared pair of electrons from the carbon. That is what it is happening in the step 2. In the step 2, the CH3CH2 OH, the ethyl oxonium ion. The oxygen is withdrawing electrons towards it, leaving a positive charge on the carbon atom. And this molecule is going to be formed in the form of a neutral molecule of water. In this step, this is the slowest step of this mechanism. There is a carbocation generated. So the step 2 is called generation of carbocation. This is the slowest step, hence it is the rate determining step. By this we can determine the rate of the reaction. Now the generated carbocation, how is it going to convert into an alkene? Let us see the step 3. The 2 carbon atoms I am just writing in the open form. Then this is what we call as the carbocation. Now the positively charged carbon is withdrawing electrons from the nearest carbon. In return it is withdrawing electrons from the hydrogen. So there is going to be a bond withdrawn from carbon and that is bonded with any of the 3 hydrogens. The H plus is removed from this carbocation containing species, generating a new double bond. These electrons, 2 electrons will be bonded between the 2 carbons forming a double bond, and each carbon got the hydrogens on them. So that is what we call ethene. So the H plus that we had added initially was eliminated. So this step in which the H plus was removed, it is called deprotonation of carbocation. To form an alkene, that is the ethene. So these are the three-step processes that are involved in converting an alcohol to alkene or the ethanol to ethene in our example. Very important mechanism. Up to now, we have discussed about the chemical reactions of alcohol. Now we are going to continue with the reactions of phenol. In our previous class, we had already discussed about the acidity of phenol. The phenol is having a pK value of 10 and it is more acidic than an alcohol. This so-called phenol that was absorbed, it is readily reactive with the base like sodium hydroxide because this is an acidic in nature. Hence, it is readily giving the H plus ions, forming sodium phenoxide ion. The sodium phenoxide ion is more reactive than the phenol. Sodium phenoxide ion is more reactive than the phenol. How means this is involved in resonance. These are already explained, but I am getting the point once again. The sodium phenoxide ion, when studied how it will be involved in resonance, the phenoxide ion will involve in bringing the negative charge of oxygen, forming a double bond between the sp2 hybridized carbon. There is a migration of pi bond onto the ortho position, and we can have the negative charge at ortho position. This negative charge at ortho position is further involved in resonance, forming a new double bond and a negative charge. This is at ortho position, and a new negative charge is at para position. And again, when it comes to resonance, a new negative charge is at ortho dash position. And finally, the lone pairs are given back to oxygen, that is the phenoxide ion. In all these resonating structures, we observe electron-rich center at ortho para and ortho dash. Where we observe the electron-rich center, electron-rich center is absorbed at ortho, para and ortho dash. Hence, at those positions, there will be an electrophilic substitution reaction. There will be an electrophilic substitution reaction. Electrophilic substitution reaction. How do we say that is it is undergoing an electrophilic substitution reaction? Here on benzene we know there is C6H6, but on the phenol we know one of the hydrogen was replaced by OH, and still there are 5 hydrogens. In which places is it undergoing the electrophilic substitution reaction? Means this will undergo where there is an electron-rich center. Where do we find electron-rich center? We find it ortho, para and ortho dash. So here these hydrogen atoms that are located at ortho, para and ortho dash will be removed in the form of H plus by the entering electrophile. So the entering electrophile enters by replacing the H plus ion. Hence, phenol is readily involved in electrophilic substitution reaction. This is an aromatic compound, so we call this is undergoing, phenol is undergoing electrophilic aromatic substitution reaction. So what is the type of chemical reaction phenol is involved in? Electrophilic aromatic substitution reaction. At what locations? At ortho, para and ortho dash. Let us see those reactions now. So let us see the electrophilic aromatic substitution reactions in the phenol. The first reaction what we are studying here is with the nitration of phenol. What this one is? Nitration of phenol. Do you remember? Nitration means we want the nitronium ion. The nitronium ion can be generated from various sources. One of the sources using dilute nitric acid or using concentrated nitric acid. Or first you can do sulfonation to phenol, then it will follow nitration. Then it will follow nitration. Here the main point is whenever you are using dilute nitric acid, it will form ortho and para nitrophenol. What are the products here we will be observing? Ortho and para nitrophenol. Any one only will be formed. Both will be formed, but we will be selecting among major among one of them. And if you use concentrated nitric acid, you will be having a tri-substitution on phenol. You will be having a tri-substitution on phenol. Let us see the reactions how they go on here. So first let us take the phenol, and once you react the phenol with dilute nitric acid, that will be generating the nitronium ion. The nitronium ion being an electrophile, it will be readily involved in substitution reaction at ortho, para, ortho or para or ortho dash. Whenever we use dilute nitric acid, we are getting majorly two kinds of products. One is called O-nitrophenol, ortho-nitrophenol. Another one is called para-nitrophenol. What is this one? Para-nitrophenol. Let us see structures now. If you observe the ortho-nitrophenol, this so-called ortho-nitrophenol will be having the OH group and the NO2 group as N double bonded O and single bond oxygen. The oxygen and hydrogen will be having an hydrogen bonding. The hydrogen bonding that is taking place within the molecule, it is called as the intramolecular hydrogen bonding. What the hydrogen bonding it is called? Intramolecular hydrogen bonding. This is taking place in the case of O-nitrophenol. O-nitrophenol. Let us compare with P-nitrophenol. In the case of P-nitrophenol, the hydrogen bonding may not take place within the molecule. It may take place between two similar molecules of p-nitrophenols. Here the hydrogen of one molecule is being attracted by the oxygen of another molecule. Means what is the type of hydrogen bonding we find? We find intermolecular hydrogen bonding. Define intermolecular hydrogen bonding. In which case? In the case of p-nitrophenol. Now, when we had reacted the phenol with dilute nitric acid, we got two products. One is called orthonitrophenol and one is called paranitrophenol. Here this is a bulky group, nitro group, and OH is also a bulky group. There will be repulsions between the group of atoms. Hence this is less stable. Whereas the group of atoms are far away from each other here, hence their stability is more. Hence we can call it is the major product, it is the minor product. Whenever we got any two compounds in a single reaction, we need to separate out them. The orthonitrophenol that has participated in the intramolecular hydrogen bonding, when compared with paranitrophenol that is formed by intermolecular, this is intermolecular hydrogen bonding. The intermolecular hydrogen bonding will make the molecules to be associated more. Hence, they are non-volatile. These are non-volatile because they have the association of molecules. But here, this is a volatile compound. There is no much association. Hence, orthonitrophenol and paranitrophenol can be separated by steam distillation. Orthonitrophenol and paranitrophenol can be separated by steam distillation. How are they separated? By steam distillation. These are separated by steam distillation. So let us see the hallucination of phenol. So let us see the reaction of phenol with concentrated nitric acid also. With dilute nitric acid we got ortho and para products separately. We had already separated them using steam distillation. Ortho is steam volatile, para is non-volatile. That is the method we separate them. But once we react the phenol with concentrated nitric acid, it is going to form, basically in this equation, there will be more amount of nitric acid, concentrated nitric acid. For the balancing purpose, we are using, there will be 3 nitronium ions generated. How many nitronium ions generated will be? 3 nitronium ions generated here. Those 3 nitronium ions will be reacting on the phenol at ortho, para and also ortho dash. The remaining group of atoms, they form 3 molecules of water. So the phenol taking the first position and the nitro groups are at second position, fourth position and sixth position. Phenolic OH is at first position, nitro groups are at second position, fourth position and sixth position. So this is called 2, 4, 6 trinitrophenol, or in short it is called picric acid. It's called picric acid. So with dilute only 2 products are obtained, ortho and para. But with concentrated we have a tri-substituted product. It's called 2, 4, 6 trinitrophenol. That's what we call also the name picric acid. Now let us see how does the phenol reacts with bromine. The phenol reacts form, we can get the ortho and para product. We can get the ortho and para product. Here you can use the bromine in the presence of Lewis acid like FeBr3 also. Lewis acid like FeBr3 also. In these cases, let us take the phenol. Once we react the phenol with the so-called carbon disulfide, which is used as a solvent, and the bromine is added in the presence of carbon disulfide solvent, which is a less protic solvent. Now the bromine will be taking place through electrophilic substitution reaction. Through electrophilic substitution reaction means when you imagine the FeBr3, the Lewis acid, we will just generally observe the FeBr3 when reacted with bromine, it will form Br plus and also FeBr4 minus. Means how did we got our bromine? We got bromine in the positive charge. Bromide in the case of net charge, we got the positive charge. It acts as an electrophile. It acts as an electrophile. So that bromine electrophile will also be generated in the same carbon disulfide solvent. Hence, that electrophile will be attached at ortho position or para position. Ortho position or para position. When it is forming at ortho position, it forms 2-bromophenol. When it is para position, it forms 4-bromophenol. 4-bromophenol. On the halogen there will be lone pairs, and oxygen also there will be lone pairs. In the case of ortho, that is 2-bromophenol, the lone pair repulsion takes place, as this is less stable and that is the minor product, whereas when they are far away, it forms the major product. So when phenol is treated with bromine in the low protic solvents or in the presence of Lewis acids, that generates a Br plus 2 ion that will be acting as electrophile that gives either two products, ortho and para. Let us see how phenol reacts with bromine in the presence of water. So let us see how does the phenol react with bromine water. Bromine water means we take bromine, it is dissolved in water. That's what we call bromine water. When the phenol is reacted with bromine in the presence of water, generally we are using 3 moles here. We have ortho, para and ortho dash. Hydrogens will be substituted by this electrophile. It will form a tri-substituted product that is called 2,4,6 tribromophenol. Whereas the remaining bromines and hydrogens, they will form hydrogen bromine. So with bromine water, we get 2,4,6 tribromophenol.